already? Okay, cool. Uh, okay. Hi everyone. I'm Harshit. I'm finally a PhD student at UT Austin. Today I'm going to talk about decision making in the language of visitations. This is uh, this is going to be about like a sequence of works during my PhD that hopefully gives you a new perspective to think about decision making. Uh, and I'm also going to introduce some new algorithms and then look at its applications in language modeling and robotics. So yeah, we can begin. I don't think it's needed here, but anyway, quick introduction to reinforcement learning. In general, we have an agent, sees the current state S, takes an action A in the environment, gets back a reward, and moves on to the next state. Right? This is the standard RL setting. The agent has a policy in mind. Every state it decides what action it should take. It can be a stochastic action or a deterministic action. And the goal of reinforcement learning has been to like maximize the cumulative discounted sum of rewards, or sometimes we call this performance of the agent. But then the problem with reinforcement learning is that we have always considered the setting of reward maximization. Uh, and in general, like if you think about how decision making works in real world, not all signals are given to us as reward functions. If I want to learn something, I can go online, YouTube, see a tutorial, try to mimic it. I can have a goal in mind. I can take a sequence of actions to reach that goal. And I can sometimes also learn from implicit preferences or explicit preferences. Someone tells me that doing something is good or doing something is bad, right? So there are a bunch of signals around us that a general framework for decision making should incorporate. Besides the fact that we do observe this variety of signals, if you're talking about reward functions and say I want to communicate some behavior to an agent, specifying why a reward function gets extremely messy. If I wanted to communicate to this humanoid agent to do a cartwheel behavior, I'll have to get an expert human engineer to write me this long lines of code. Uh, and even if they do write something sensible that looks sensible, when you optimize on it, the reward function, the RL can hack the reward function and give you policies which don't make sense. But then a natural argument here is that maybe we have this reward hypothesis, which says that probably every learning signal may have an equivalent reward function. So maybe we should go about given a learning signal, we should try to recover the reward function. This should be our general rule. But then the problem is figuring out this algorithm to go from learning signal to reward function may be as hard as solving the RL problem. And it is actually the case with a number of learning signals. So then what have we done in the past? We have created different kind of algorithms to deal with different kind of learning signals. For example, demonstrations, preferences, goals, and so on. We have a bunch of different algorithms that individually tackle these different learning signals, and they're like carefully constructed for that purpose. But an ideal framework for decision making should look something like this. We have a bunch of learning signals in the environment. Uh, we have like a unified way to specify those problems. What do we want to learn from them? And hopefully we have unified algorithms that basically take those learning objectives and optimize them efficiently. And ideally, like if possible, we wouldn't want to learn reward functions as an intermediary. We can directly go to optimal policy, which is what we care about at the end. And one of the reasons we want this unified problem specification is that sometimes in the real world, we want to learn from multiple learning signals at once. Or maybe you're in a situation where learning from one environmental signal is better than the other environmental signal. And our framework should be able to deal with all kinds of things that we see. So the main topic of this talk is basically if there is a common framework to express and solve learning from a variety of environmental signals. Uh, I'm going to break down this talk in like three parts. First, we are going to see how we can specify decision-making problems in this language of visitations. Then I'm going to talk about how to optimize those visitation objectives. And finally, I'm going to talk about how that same framework that what I'm going to introduce will allow us to go towards an completely unsupervised objective for reinforcement learning and also allow us to uh, do test time policy inference in a zero-shot manner. Okay. Um, yeah, before we start and go to the formal framework of how to specify a decision-making problem in visitations, let's build up some intuition. And for this, like we are just going to use preferences and demonstrations and going to see like how if I write them as problems or visitations, they are basically one and the same problem. Okay, so right now we are only focusing on the first part of the talk, where how to write things in a unified way. Yeah, before we do that, we should be on the same page about what visitation distributions are. Uh, the way state action visitation distribution is defined, it is the probability. It's the discounted probability of visiting a particular state S in the environment and taking an action A from that state. And this is under a particular policy pi. So intuitively, like you have an agent here. Let me enable the pointer. You have an agent here, and this heat map basically shows like if it follows the policy it has in its mind, where it's going to end up, which states it's going to end up. So this is the state visitation distribution of the agent. In reality, we don't have this like closed form solution of where the agent is going to visit. We or like we have the entire distribution. In reality, we have like empirical samples of where the agent visits, and those are basically the transitions that the agent encounters in the world. And for example, this may be like a sequence of trajectories that the agent performs in the world. We take that and put that in a buffer, and those becomes our uh, empirical agent visitations. Yeah, mathematically, it's basically just a discounted probability of reaching state S and taking an action A. One thing that's going to come handy later on is this policy visitation uniqueness. Basically, if I have a policy pi, it's going to induce a unique visitation distribution in the world. And if I have a visitation, I can quickly get the policy that corresponds to that visitation in a closed form. So going from visitations to policy is quite easy. So if I have, say, an optimal visitation for some problem, then I can find the policy very quickly. All right. Yeah, let's start looking at some environmental signals. So we have expert demonstrations here. Here the agent is trying to show you how to do a cartwheel. Or we can have preferences where a human tells us between two behaviors. Maybe this one is not making progress towards a cartwheel behavior, and this one is making doing something more similar to a cartwheel. So this form of signal is basically preferences. Expert demonstrations are usually quite nice because they describe the expected behavior of the expert in the environment. But preferences are like really easy to obtain. So preferences can enable this data flywheel. We have all seen this with ChatGPT. Like it's a very easy signal for a human to provide, and we can do continuous improvement of our agents. So then what's the problem if you have these two learning signals? Right now, if I want to deal with learning from demonstration or preferences, I have like a whole other set of algorithms, hyperparameters, tricks, and theory. As an example of hyperparameters, I'm just putting some on the slide here. We have to tune a whole different set of hyperparameters, which are like mostly disjoint. Now, let's see what happens when I start looking at this from the perspective of visitations. So from the perspective of visitations, if I'm given a good preference and a bad preference, then all I need to do is ensure that under my good preference, I have a higher return than the bad preference. If I'm given expert demonstrations, all I need to do is ensure that under my expert visitation, I have a higher return than the current policy visitation. So from the perspective of visitations, both are basically solving the same ranking problem between a good preference and a bad preference. With this unification, like you already have an algorithm in hand where we can have a reward player and a policy player. The reward player's job is going to satisfy pairwise rankings between a good preference and a bad preference. All it has to do is like make sure that a good preference has a higher return. And then the policy player's role is going to be, as usual, maximize the reward function. So this is a very straightforward algorithm. Reward player is learning something which ensures the ranking hold, and policy is maximizing the reward function. The way we satisfy these rankings is basically by something we call a ranking loss. It's actually quite straightforward. For the good preference, we are regressing the reward to a scalar k. And for the bad preference, we are regressing the reward to a scalar 0. So this loss was actually a deliberate decision because first, it has a good empirical properties. For deep RL, this is quite good if we can learn a bounded reward function. Uh, Second is like we actually show that if you optimize this loss and when you play this two-player game, it will converge to an equilibrium which has a bounded F divergence with the expert, or it does something very similar to the expert at convergence. We are going to use this notion of F divergence again and again throughout this talk, so I'll just like quickly mention what that is. F divergence basically captures a distance between two distributions, here between P and Q. So here we have the P distribution denoted by red, and we have the Q denoted by green. And on the right plot, we are showing how the F divergence evolve as the Q distribution goes towards the P distribution. So as they get closer, F divergence decreases. So we apply this straightforward algorithm that I just described to uh, to a particular setting where imitation learning fails. And this setting is basically we are considering some hard exploration problems, and all you are given is action-free demonstrations. So if you just learn from action-free demonstrations, it's basically state, next state, and the next state after that, and so on. You have to explore a lot before you end up with something that resembles an expert. And in this setting in particular, if you add a handful of preferences, this can really help guide policy learning. So that's exactly what happens in this case. Like if we use our unified framework to learn from preferences and demonstration, treating the preferences as just like additional data points, you can solve some of these hard exploration tasks, which were not possible with purely imitation learning. This work also was recently used for alignment because I think as soon as I introduced this notion of like you can learn from demonstration and preferences jointly, this is one thing that the LLM community does in two stages. So this recent work tried to use our framework, modify it for the setting of language model alignment, and learn from preferences and demonstrations jointly. On our side, we applied this to this problem of scalable mapless navigation. I'm going to show some results first and then going to talk about what we exactly do here and why our approach of this unified learning helps. So this problem is basically you have got unstructured map, unstructured, you have to navigate in an unstructured environment, but you don't have HD maps with you. These are like generally you assume you have HD maps and you have autonomous vehicles. But in this problem, you don't have HD maps and you just have to navigate based on your local understanding. Uh, so yeah, here the bottom right basically shows the reward function that our method produces on the local cost map. Um, yeah, let's see. So in this example, we were doing a long horizon navigation of 2 kilometers. And the way we evaluate our method is how many times did you require an intervention? So if your robot starts doing something weird, you want to give an intervention and correct it. That's like you suffer that one cost of intervention. Yeah, so what we are doing here, or maybe first, what prior methods do to solve this problem is basically they collect expert demonstrations. Once you have the expert demonstrations, they do behavior cloning. But the first problem here is obviously we don't know why an agent is doing a particular action if it's doing that, so we can't really debug anything. And then behavior cloning is not the most robust strategy when you have a few set of demonstrations. So with what I've just described, uh, what we can simply do here is we can create a same set of expert demonstrations that this behavior cloning methods use. So we collect those demonstrations in the environment, take them offline, and ask humans to annotate counterfactual preferences, like what they like in the environment. If the robot has done some, like they can just draw on the map, like if you had done something like this would have been terrible. If you had done something else, it might have been better. So with the same set of data, you can create much more data points that you can help for learning. So once you can annotate with preferences offline, we can train the reward function using a similar method to what I just described. Uh, so this was a test on 2 kilometer navigation in an unseen environment, and we required one intervention here. And this is like quite like strikingly different to what prior methods require, because most of the methods that exist or the ones we tested, the state of the art ones, they required at least like 17 interventions. And what we realized is that the reward function that we learned because of all this like counterfactual annotations, it was quite robust. Like it could detect narrow curb and crosswalks. It could identify foliage covered sidewalks. It can detect pedestrian and tight corners. So that was quite good to see. All right. So far, we have just like built the intuition of like how we are going to unify things, why visitation helps. But now we are going to formalize it more and hopefully get rid of the reward function inference in between. Uh, at this point, like, are there any questions?
Yeah, I have a question. So, does this problem formulation assume you are operating in a finite set of states? And
Uh, mhm.
the agent also, like if you're working with observations, then constructing state would become extra problem, right?
Yeah, there are like two things you mentioned here. First is like the finite state. Um, y- so this like almost like all our experiments are going to be in continuous states. Second is more about like partial observability. Uh, yes, this framework does not handle that as at the moment, and that is something that we are actively looking in. How do we make if we can put that in the same framework, and how do we understand it better? Right now, if we encounter a situation where maybe if we are learning from images and we don't understand what the state is, we'll just like stack together state images from the past or do something that makes us basically near Markov. Uh, yeah. All right. So let's move on to maybe a broader set of problems and how do we unify them in the language of visitations. So maybe the first thing we should do before moving forward is see how to do reward learning in terms of visitation, because that is sort of backwards compatibility. If you are going to propose something new, it should obviously work with reward functions. In terms of reward, this is basically a straightforward problem. In visitations, so you want to find a visitation induced by some policy pi such that the expected return is highest, which is the visitation times reward. And but this is not really an optimization problem because I don't know what is the set of valid visitations in the environment. Uh, because it has to be induced by some policy pi. And then once I deploy a policy pi, it has to satisfy the dynamics of the environment. So I only have to search within the feasible set of visitations. And the way we convert this into a proper optimization problem is basically relaxing this assumption that my visitation should be valid in the optimization objective, and then adding a constraint which forces the visitation to satisfy the dynamics of the environment. This is basically called the Bellman flow constraint. This kind of formulation was explored quite from like in 1960s, but we are going to give a new way to optimize this objectives. Okay. So there are some good things about this objective that is typically we don't see this in RL. It's a linear and like it's a convex optimization objective. It has linear constraints. So these are the class of methods that we know how to solve in convex optimization. Okay, we can express imitation learning in terms of visitation. Imitation learning is basically matching your agent visitation to an expert visitation. And because this distribution over state actions is unconstrained here, I have to ensure they remain valid. So I add the Bellman flow constraint. This Bellman flow constraint will be added everywhere to make sure the visitations that happen in the environment are valid. You can do goal reaching in terms of visitation, which basically turns out to be matching a distribution between your current agent and a distribution that puts all of its probability mass over the goal. So if I minimize this divergence, then I am basically solving a goal reaching problem. I can learn from preferences in terms of visitation, which if I'm given a good preference and a bad preference, uh, all I have to do is ensure that my agent visitation on the good preference is more than agent visitation on the bad preference. So it does the good thing more likely than the bad thing. In fact, a large class of problems can be written as convex objectives over visitations. And here I list a few of them, but there is this paper from Tom Zavi, which is a very nice read if someone is interested in how to. Uh, that paper was not really intended for unification. That paper was intended to give a algorithmic reduction of like uh, how to solve convex problems of visitation using RL formulation, but it's still quite relevant. Okay. So I've introduced a bunch of objectives that basically take this like general form. You have a convex objective or visitation, and then you have this linear constraint. And now the question is, how do you go about solving this visitation or objectives of visitation? So we have seen the first part, how to specify this problem in a unified format, and now we're going to come to unified algorithms to solve those, and hopefully without intermediate reward learning. Uh, For this part, we'll restrict our attention to the regularized RL problem, uh, where the objective is to maximize this return while also making sure that your policy visitation remains close to some offline visitation. Uh, so while the set of tools that we are going to develop will be applicable to any convex objective, looking at this particular regularized RL problem will help us deal with a lot of environmental signals that we care about. I'm going to show how in the coming slides. Okay, so as a quick exercise again, let's see how to write the regularized RL problem as a convex program. So you have your return maximization, and then you have stay close to some offline data visitation, offline state action visitation. We have to ensure that this DSA remains valid, this visitation remains valid. And actually, there are two ways to go about this. One is by imposing a state action constraint, and the other is a state only constraint. These are just like two forms of Bellman flow equations. If you impose either one of them, you are guaranteed that you will learn the optimal visitation. So you can go about using any of the constraints that you like, and they are going to give you the optimal visitation. And as I was saying earlier, we have this convex objectives and we have linear constraints. And this is something we know how to solve well using Lagrangian duality. So I'm going to apply Lagrangian duality to these problems, get a dual form, and see if like they are basically easier to optimize. Because we have this optimization here and then we have constraints, and generally dealing with constraints like this is not a very good idea. We want something which is an unconstrained optimization. So if you do a little bit of algebraic manipulations, apply duality here, you get two class of methods. One is dual Q class of methods if you use the state action constraint. If you use the state only constraint, you have dual V class of methods. So diving a little bit deeper, our first objective is basically the dual Q class of methods. Uh, so what we have here is basically uh, a second term, which kind of looks like Bellman error. We have like reward plus next queue, gamma discounted next queue minus the current queue. But then we also have this like conjugate of F divergence, which looks a little bit weird. Uh, but the basic intuition to get here is we have this objective, which is basically max over pi and min over q, which is like what we see in actor critic uh, objectives for RL. But with the good thing here is that we only need to sample from the offline dataset that we regularize against. So this is a purely off-policy objective. So that's like one good thing. Second is that in contrast to typical methods like SSE or TD3, which basically give you an optimal policy and the optimal Q function, here you get something extra, and that is basically the optimal visitation, which is where my optimal policy is going to visit in the environment. I get a distribution over states and actions that the policy is going to visit. And that optimal visitation can be extracted by a simple transformation of the learned Q function. Okay. On the other hand, if you use state only constraints, we get this other class of methods that we call dual V learning. And this is somewhat more interesting because if you see here, there's only one variable involved in the optimization. So we don't have to worry about solving a two-player game to solve RL or any learning from decision-making objectives. We just have to optimize one variable and that's it. So that makes learning much easier. Again, the first thing to note is this is naturally off policy. We get optimal visitation as before, but the most like salient feature is that we only have to optimize one variable and we get to solve our decision making problem. So the first thing that we do is, again, just a sanity check. We apply this to learning from rewards. And when we do that, we observe like on this setting of D4RL, which is for evaluating offline RL algorithms, we already see behaviors that are we do slightly better or we are competitive in most of the domains compared to state-of-the-art methods. And recent works that build on top of our method are even like better than what we report here, and they exceed state-of-the-art non-dual methods. Okay. Uh, we have introduced a new formulation of like in terms of visitations, and then we've seen how to optimize them for rewards. And now we are going to move on to other environmental learning signals. But just before we do that, any more questions so far?
Questions, audience. There's nothing online.
Okay. All right. So let's move on to demonstrations. Uh, if you notice the regularized RL problem, we had this like return maximization objective and F divergence between the agent and some offline distribution. So if I just set the reward function to 0 and change this offline visitation distribution to expert distribution, then this becomes an imitation learning problem, right? So, and I can use the same set of tools that I've developed so far to solve imitation learning. And in fact, like when we do this and we derive the dual forms, we realize we can finally understand a lot of prior methods that were derived using different mathematical tools, motivated using like uh, different intuitions. They are basically all part of like dual algorithms for solving imitation learning. Some of them are listed here on the right side. But we were not really interested in this problem. We were interested in a, a more practical setting for imitation learning where you are given like expert demonstrations, but you also have a non-task relevant transitions in the environment. So what I mean by that is like maybe more intuitively, suppose you're trying to learn how to play baseball. Somebody is like showing you how to hit. Uh, when you go towards learning that, you have like all this prior uh, experiences in your mind that basically help you in imitating that task better. Like you might have picked sticks earlier, and that helps you do better for imitation. And that is the kind of setting we are interested in. We have some suboptimal data from non-task relevant transitions, and we have some expert data. So this brings us to our method recoil, which is imitation learning with suboptimal data. It's going to be same principles again and again. So that's why I'm like moving a little bit fast here. Um, we are still trying to match our agent visitation with the expert visitation. All I have to do is add suboptimal data on both sides of this distribution matching objective. This basically becomes a mixture distribution matching objective. So first, it still remains a valid imitation learning objective because the global minima is still when the agent matches the expert completely. Second, we already see like we can incorporate arbitrary off policy data that can help in imitation learning. And we actually show that adding this data can improve imitation learning performance theoretically. So with this, we have a primal objective for imitation learning with suboptimal data. It looks very similar, like we still have F divergence and we have a constraint on my visitations to remain valid. Uh, if I apply the same set of tools, I get a off-policy dual objective for imitation learning. Uh, I'll give a quick intuition on what this looks like. So if I expand this like dual objective for a particular divergence, here I'm doing it for chi-square, it looks something like this, where I'm learning a Q function which is higher at the expert, and then I'm learning a Q function which is pushed down at the places at the actions suggested by my current policy. And then I'm trying to satisfy a Bellman consistency with a zero reward function. So this is basically what's helping us with the recoverability. So if I'm at the bad regions of the state space, how do I get to the regions with the high Q function? The third term is basically helping me with that. So this is just like an overall intuition. And again, this is sort of hand wavy, but this is the exact dual objective that if you optimize, you can get a policy that basically solves imitation learning. Okay, we apply this to a bunch of manipulation and locomotion domains, and particularly for high dimensional manipulation tasks, all of the prior methods that are basically trying to do imitation learning with suboptimal data, they almost get near zero performance. And one of the reasons is that they're trying to predict a reward function as an intermediate. So if you predict reward functions and there's like a little bit of mistake in that, maybe you overfit, and then you train your policy on that reward functions, you are going to do quite bad. So this is like something that's useful to where you can directly go from your expert demonstrations to policy without ever inferring the reward function. Just like illustration of what happens with this prior methods. Uh, when they're trying to do imitate here, like they're trying to hammer a nail, when they make an initial mistake, they're not able to recover, while the method that, well, recoil is able to complete the task, recover from like any mistakes it makes. Recently, this method was also used for LLM fine tuning. And the idea here was if we can do visitation only, if we can match visitations instead of just matching policy, we can do slightly better than the traditional behavior cloning way of uh, SFT. Okay, so we can move on to another learning signal, which is goals. And basically the problem of goal reaching is given an initial state. You want to reach to a goal position as fast as possible. And in this setting, we can, uh, as I described before, you can still formulate this problem as distribution matching between your agent visitation and a visitation that is centered over the goal. And such a distribution matching problem is basically solving max entropy goal reaching. So with this, you can similarly formulate objective which can incorporate suboptimal data. You can get the dual, and you get a dual objective for goal reaching. In this particular domain, or in this particular setting of goal reaching, we wanted to evaluate scalability. So we considered high dimensional observations like learning to reach image goals, and when you have like offline data set of transitions, which is of suboptimal quality. In this setting in particular, like you have no single trajectory that reaches the goal, and you have to stitch together a lot of trajectories to reach that. So what in some of the hardest tasks, the prior methods completely fail, while we still observe some successes, which is good because this indicates like our method actually works with high dimensional observation. And then more recently, we wanted to try this on real robots. If this method is actually suitable for training in real world. And here we were interested in another learning signal, which is action-free demonstration. So you can imagine like somebody gives you a demonstration, like a human basically shows you how to do something. So you have a bunch of states and you want to imitate how to do that with a robot, and you don't have what actions the robot should take. So in this case, if you impose the visitation constraint on S and the next state, you get a dual which is going to be an action-free dual. So when I optimize this dual objective, you only need to sample S, S prime, and the next state after that. Again, like the intuition here is that all you need, the next state basically leaks information about the actions. So instead of, because you're not given actions, you can basically use next state as a proxy to get informations about the actions, missing actions. We tested this for cross-embodied demonstration where somebody shows you how to do a thing, and then the robot has to figure out the intent and solve this imitation problem. So this is more of a static example, but in this case, we were trying to do expert hitting of a falling puck from top of the board. The air hockey board is tilted, and this is our method. This basically, the interesting part was it actually learns the human wants to like go back, get into position and hit it. So it has like, with a few expert demos, it has figured out what the intent was and is able to replicate that quite nicely. Okay. So far, we have seen like how to optimize this visitation objectives, and they work on real robot, high dimensional observations, and so they're scalable. We can move on to the last part of the talk, but I'll briefly stop here if there are questions.
No questions, Ashik.
Okay. So far, we have been looking at a problem like this. We have a convex objective, and then we have a constraint, which is sort of a linear constraint. So the convex objective basically tells you what we want to basically is an objective for learning from a particular environmental signal, right? And then we have this constraint, which ensures your visitation remains valid. What if I just like forget the convex objective and nobody is giving me any learning signals, and all I have is a bunch of transitions in the environment? So in that setting, I can, if I just look at the constraint, this gives me something interesting. First, this constraint is linear. So this tells me that if I want to find all possible valid visitations, I can, it should be relatively easy. And it, so because it's linear, all possible solutions of these visitations are going to form an affine set. So that is like the primary observation of this work below, that we can just like forget the convex objective and just look at the constraints, and those constraints, I can characterize the whole set of feasible solutions of that constraint. What I mean by affine set is that any visitation I can write it down as phi times W plus B. Basically, all valid solutions of reinforcement learning or for decision making, they lie on this hyperplane given by phi W plus B. And W is like a vector uh, of some fixed dimensions that we decide. So this is where we lose information when we are learning to represent all possible visitations. But changing W basically will give me different visitations for different policies on this plane. So if somehow I can find this phi and B, which are these immutable properties of the environment, this phi and B only depends on the MDP. It has nothing to do with the policy. So if I can find phi and B, then I can do a lot of decision-making tasks very easily. Say I wanted to do imitation learning, zero-shot imitation, and somebody tells me that I want to imitate a state-only visitation distribution of an expert. So somebody gives me observations of the expert. All I have to do is find a W such that phi W plus B matches the expert visitation distribution. And this can be done purely offline if I have offline samples. This is basically just linear regression. So I've so what we have done here is basically put all the complexity of reinforcement learning or decision making into a pre-training part where I have reward-free transitions and I figure out what phi and B is. And once I've done that, then given any decision-making problem, I can quickly solve it without actually doing any further solving any planning problem during test time. So we put this idea to use in a more practical setting where we were interested in going from language to behaviors. Um, in fact, this what I presented before is like one way to do zero-shot RL. There are multiple ways you can do it. There's like the forward-backward algorithm. There's Hilbert representations. So there are a bunch of ways, and actually all are applicable here. And what we are trying to do here is if someone tells me or someone tells an agent an instruction in language, here like we are told to do a lunge behavior, then I can ask, say, a video foundation model to show me what a lunge behavior looks like. So in this case, a lunge behavior video foundation model is basically showing how a lunge behavior look like, just the observations. We don't know what actions I need to take to actually get this behavior. And this imagination of video foundation model can be in the domain of the agent or can be in some other domain, and that's totally fine. And then once you have this sequence of frames, you can treat this as an expert and use all the principles that I described about to do zero-shot imitation. In this case, we just need to find a W such that I match this expert visitation. So here are some results from this method. We don't do any test time training. We have collected data using R&D in most of these environments. So these are random exploratory data, and there are no meaningful behaviors that we have encoded specifically. And at test time, we ask the agent to do like give it like some weird language commands that we want to see how the agent performs. And if I tell the cheetah agent to do a bunny hop, we get something like this. For ant, we asked it to do cartwheel. It does something to the best of its ability. In this case, crawl like a worm for this walker agent, or headstand for this 2D humanoid. Note that this is like without any test time training, and there is no, it's all like instantaneous. If someone gives me a language, I can give you a policy in like few seconds. Basically, what time it takes to do a single forward pass. Okay, and it's not just limited to language. You can take any video from YouTube and get a behavior that matches that YouTube video. In this case, we have a 2D humanoid trying to do some yoga poses in a zero-shot manner. This was really cool. We took a video of cartwheel from Wikipedia, a WikiHow, or like how to do a cartwheel, and we have this animation, and we give this to a 3D humanoid agent, and it does that pretty flawlessly. Similarly, here we have results for running. And yeah, this is what we get. Yeah, this brings me to the end of my talk. I have some references here if you want to check out some of the recent works. Uh, and yeah, these are all the collaborators that helped me do this work. So I'll stop here for any questions here so far.